This is problem 217, page 59 in Sears and Szymanski, University Physics. So it says we have a car's velocity as a function of time is given by the x component of the velocity, so this is a one-dimensional problem, is equal to alpha plus beta t squared. And alpha is a constant, 3.00 meters per second. Beta is constant, 0.100 meters per second squared. Cubed. It couldn't be squared because it wouldn't work out right. So double checked because I've got seconds in terms of time, so seconds squared times meters per second cubed gives you meters per second. Calculate the average acceleration for the time interval from t equals 0 to t equals 5. Calculate the instantaneous acceleration for t equals 0 to 5. Draw the v sub x and a sub x graphs of the car motion between 0 and 5 seconds. Okay. So to calculate the average acceleration, remember average acceleration is equal to the change in velocity. So we're going to do it v sub x at 5 seconds minus v sub x at 0 seconds divided by 5 minus 0 seconds. So it's the velocity at the end of the time interval minus the velocity at the beginning of the time interval divided by the time difference. So we need to evaluate this expression at 5 and 0. So let's just go ahead and put the constants in. So alpha is 3 meters per second plus 0.100 meters per second cubed times t squared. Okay, so v sub x of 0 is just equal to 3 meters per second because the second term will go to 0. And v sub x at 5 seconds is going to be 3 meters per second plus 0.1 meters per second cubed times 5 squared. And so that's 5 squared is 25. 25 times 0.1 is 2.5. 2.5 plus 3 is 5.5 meters per second. So the average velocity is going to be 5.5 meters per second minus 3.0. Make sure I have enough significant figures. Divided by 5 seconds. 5 minus 0. So the average velocity is 5.5 minus 3 divided by 5. That's 0.5. So it's plus 0.5 meters per second squared. Okay. So that's the average velocity. Now there is a calculus way of doing it where you calculate the average velocity by integrating the average acceleration by integrating the instantaneous acceleration, but that's not what they're looking for here. Then it says calculate the instantaneous acceleration. So that's an equation. So part B is an equation. And what we do is we say that the instantaneous acceleration is the derivative with respect to time of the velocity. And the velocity is alpha plus beta t squared. So here it is right down here. This goes to 0. The derivative of t squared is 2t. So 2 times 0.1 is 0.2. So we get 2.200 meters per second cubed times t. So that's the equation for the instantaneous acceleration. So t equals 0, the acceleration is 0. And at t equals 5, the acceleration is going to be 1. And actually the average of those two numbers, if I take the average of the two accelerations, I'll get 0.5. But what they're asking for here is the equation. Pretty sure. Let me just check the answer here. Well, actually they have a number, so oh, it says calculate the instantaneous acceleration for t equals 0 and t equals 5. Okay. So the instantaneous acceleration for at 0 is going to be 0 meters per second squared, because I put 0 in for t and I just get 0 times 0.2. The instantaneous acceleration in 5 seconds is going to be 0.200 meters per second cubed times 5 seconds, and that gives me 1.00 meters per second squared. So that's at 5 seconds. And if I, instead of the average acceleration, if I ask for the average of the instantaneous accelerations, at t equals 0 and t equals 5 seconds, you see, I average these two, and I'm going to get 0.500 meters per second squared. So the average acceleration and the average of the two accelerations gives me the same number. Okay, I guess that's it. All they're asking for. I'll draw the V versus T and A versus T graphs of the car between 0 and 5 seconds. Okay. So let's see. The velocity is going to start out at positive, and this will become more positive. So this is V sub x of t. Here's t. At t equals 0, it's 3. Here's 6. So I'm going to draw a dot right here. And at, let's pick a, let's say this is 5 seconds. So we go up here, about there. So it's a little bit less than 6, 5.5. As we go back here, we've got the velocity at 5 seconds is 5.5. Now it's going to be a parabola. It's not going to be a straight line. So we're going, and the acceleration here is 0, so the slope is going to start out at 0. And it's going to kind of curve up like this. Now, as far as the acceleration versus time, the acceleration is positive. Here's 5 seconds. This is acceleration. The acceleration function of time starts out at 0, and after 5 seconds, it's up to 1. So this is 1 meter per second squared. Let's go back up here and label these. So this is 3 meters per second. This is 6 meters per second, and 5.5 is going to be about right there. So in this case, after 5 seconds, you're going to be at this point. As you can see from the equation for acceleration, it's just a linear function that goes through 0. So it's just going to look like this. Extrapolate if we want to. So that's what they both look like. Kind of different. I mean, normally if you have constant acceleration, then the velocity is linear and the position is parabolic. In this case, the velocity is parabolic, and therefore the acceleration is linear.